This short video is going to give you a second example for doing regressions in R. So this is an example that I call the maintenance cost example, and it's an absolutely tiny example. So the example consists of 5 observations. So here is how I've entered in those values. So you'll see that I have an object over here called machine. I did this before starting the video. And what this data set has is 5 machines. So the sampling unit is a machine. You know the age of these machines. So machine number 1 is only 2 years old, whereas machine 2 is 5 years old. You also have the maintenance cost in thousands of dollars. So what is the annual maintenance cost for a 2-year-old machine? Well, it's about 6. So let's run quickly through all of the tasks that we do with regression. So the first is we probably want to look at a scatter plot and just make sure that the data look okay. So to do that, if we just plot the object and look at our scatter plot, and we see a strong positive association. So what the scatter plot tells us is the older the machine, the more it's going to cost to repair it, to keep it running. This could be corroborated by running a correlation, and so we see a correlation of 0.98, which is huge, telling us the same thing. Now, if we wanted to fit a linear model, we would say fit is equal to LM. Remember, you always start with the dependent variable, cost tilde age, and then you have to give the data set name. So here's our fitted object, and if we do a summary of fit, we get various information about it. If we do an AB line fit, it superimposes the estimated regression line on our scatter plot. So what is the equation of this line? Well, the equation of the line is going to be minus 1.06 plus 2.75 times age. Now, we might want to interpret these coefficients. So what does 2.75 tell us? 2.75 tells us how much we expect costs to increase for every additional year that the machine ages. Okay, so if we go from having a 2-year-old machine to having a 3-year-old machine, we expect to spend an extra $2,752 to maintain that machine. What does the intercept tell us? Okay, the intercept is minus 1.06. This is, well, rather counterintuitive, but let's take a look at the literal interpretation. So the literal interpretation of the intercept is a machine that is 0 years old costs minus $1.0645 thousand to maintain. Now that doesn't make any sense. So we take the machine out of the box, and we're going to get a refund of $1,000. It doesn't make any sense. So what's going on with regression? Well, what's going on is a very important point, and that important point is this: beware of extrapolation. Beware of extrapolation. So notice the value 0 isn't anywhere on the scatter plot. So scatter plot starts at 2, ends at 9. The relationship looks very linear between 2 and 9. However, outside of this window, this 2 to 9 window, all bets are off. So 0 is out here someplace. We don't have any data to say what's going to happen at 0. If we extrapolate with that line, it's going to go through minus 1, but that's probably not realistic. On a similar similar point would be if I asked you to estimate what it's going to cost to maintain a 50-year-old machine. Your answer should be, I don't know, because you don't have any data beyond 9. All right, so don't try to interpret that intercept in this case. Now, how could we find a 95% confidence interval for the age? In this case, our data set is so small, don't go 2 standard errors. It's going to be a bit more than 2 standard errors. Use the confint formula. And so what you'll see is that you think the slope is somewhere between 1.8 and 3.65. Another question we might want to ask is there a significant relationship between age and cost? So in other words, is it plausible that the slope could be 0? Well, the way we would answer that question is simply to look at the p-value. P-value is less than 5%. I should also point out R puts stars by significant results, so that double star means that p-value is less than 1%, indicating it's highly significantly different from 0. So we can reject the null hypothesis that age has no effect on cost, and we conclude that as the machine gets older, it's going to cost us more to maintain it. Now, we could be asked to forecast. For example, what does it cost to maintain a 6-year-old machine? We don't have any data there, but here we're interpolating, not extrapolating. So to do that, we'll just use the predict function. So predict fit and data.frame age equals 6. So we would expect to spend about $15,000 to maintain a machine that is 6 years old. Now, if we wanted a prediction interval, we would just say interval equals prediction. And so what is this telling us? Okay, among 6-year-old machines, the lower bound would be about 9,000 if you have a really good machine. The upper bound would be about 21,000. So you're not going to have to spend more than about 21.5 for a 6-year-old machine. If you wanted a confidence interval for the mean, type in confidence here. So this is coming back to this estimate of 15.45. How much variation is there around that estimate of 15.45? Well, that mean could be as low as about 13 and about as high as about 18 is the way to interpret that. And that's about it for the common tasks that we do with